So in neural network, the way we need to, by default, it's going to initialize with zeros and all. You can see that the activation, apart from activation, we can even add you can see the ReLU, ELU, or SELU, the other option that we discussed yesterday, right? Even we try with the leaky ReLU, but you need to create an object for leaky ReLU before you provide this to this one. Here, by default, it's ReLU. Stick with ReLU. No need to make any changes unless in exceptional case, change so leaky ReLU or a SELU. And we discussed about HE and Xavier initializations, how to initialize this parameters in the first phase. So initially, we usually go with zeros. So then now we have better options: HE normal, Xavier normal, Xavier uniform, or H uniform. So normal in the sense, all the parameters that it is going to generate is going to be normalized form, whereas H uniform is going to be, all the values are going to be the same constant. The remaining is just fitting and learning history. Yesterday, we thought of discussing the dropout. Yeah, the overfitting is one problem we already have. So overfitting is nothing but understanding even the noise. So in the case of outliers, sorry, in the case of outliers, there is a possibility that we can remove it in the early stage itself. But just imagine that if there, it has not, I mean, we even after we remove outliers or anything, any other step, just imagine that we have amount of amount of noise in the data set. Then we call it as overfitting, isn't it? Usually we will understand it by looking at train loss or validation loss, or train accuracy or validation accuracy. In train accuracy, we'll get better accuracy, whereas when we apply it on validation or test data set, then it's going to be very meager, very less. Let's take the train accuracy or loss. Train accuracy is around 99%, whereas validation or test loss or test accuracy is somewhere around 50 or 60. Then definitely it means that overfitting. So there are many ways to solve the overfitting problem. One is when we have very less amount of data, there is a possibility that the model may be overfitted. So we have to have a lot of data so that it can build a more generalized model. Another one is regularization. Regularization is a kind of penalization. We have seen L1, L2, right? Early stopping is idea. Let's take we have given 1,000 epochs. Okay, when we give 1,000 epochs, for example, let's take that after 150th epoch, the accuracy is 85. Okay, so let's imagine that 149 itself, 149 step itself, we got 85, and 150th it is 85 again. 151 it is going down. Let's take 83. 152 going down, or maybe constant. Basically, the idea is after certain number of epochs, if it is constant thereafter, or it is been decreasing, then it is better to stop right at 149th loop itself, right? 149th epoch. So that is what the whole idea of early stopping. We can stop at an early stage itself, but we need to give patience. Patience is how many epochs that has to wait to see like whether it is been decreasing or constant. For example, let's take I have given patience 2. So 85 and it is constant 85 again and it is decreasing. So it's going to stop right here. Early stopping is going to stop right here itself. There is something called checkpoint too. Checkpoint is, so every epoch it is going to save the model in our disk. And when we combine early stopping with checkpoint, what happens is it's going to stop right here. The problem is going to pick this model. So when we combine with checkpoint and pick the we have a load of models, right? A series of models. So it's going to go back and pick the best model or this one as it is constant. So it's going to pick this model. That's the last best model. So checkpoint is going to keep on saving the models. I will explain how to do that. So before we get into it, increasing data, of course, you need to ask client or you need to find some other source to get more data if it's not sufficient. Another one is L1, L2 penalization or regularization. We discuss in detail in ML internals. The same idea, nothing different. The way we apply it's going to be different in the case of you know uh, deep learning. And let me show you that. When it comes to okay, so let open it. Registration, right? When it comes to declaration, you can yeah. So here is then this is normal one without declaration. And this one is where we apply this regularizers. Declares one, L1, or we can even apply L2. Okay. Of course, we can change this proportion. Let me put this.
L1, L2 is like lasso ridge, that one, right?
Lasso ridge of machine learning algorithms. Here
Yeah.
in deep learning, we are applying this concept. The L1, L2 is because actually penetration concept. We applied in lasso and ridge algorithms. We should not combine both. Here we are applying L1 regulation and here we are applying L2 regulation. This is the way that we can implement L1 and L2 regulations. And dropout is a one most another important topic. It's always going to be very confusing, especially for beginners. It's going to drop out a certain number of neurons in every loop, every epoch. For example, in this layer, let's say that we have given 0.5 as the dropout. That is 50%. It's going to drop out 50% of neurons while training. It's randomly going to drop out. In the second epoch, it may not be the same number of neurons. Same neurons. It can be some other set, but it's going to 50% neurons going to stop. Drop out. The reason why we need to drop out those neurons is, for example, let's take bear. For example, let's take that this is the data set. This is the input that I have given. Okay. So if we give this input, just imagine that we have built a classified model so that it has to classify whether it is tiger or bear, or maybe bear or fox. So in that case, we will give proper images, bear and different set of images of bear and different set of images of fox. In that case, what happens is like we are not going to add this sort of noise to that. Removing noise is one thing, but in some case we need to even add noise to make sure that if okay, once we have the model, just imagine that if this is being fed as input to the model to predict whether it's bear or fox, what is going to happen? So it may not predict well because it's behind the tree. This tree by itself is a noise.
Nice.
So if we drop out neurons, basically what does that mean? We are intentionally adding noise. We are intentionally taking off certain amount of information. So when we drop out it, then we can even able to detect this sort of predict this sort of image as clear as bear, right? That is the whole idea of dropout. So it's going to randomly drop out. So it's not the same neurons. In every epoch, it's going to change. Here we have only 4 neurons, but obviously we are not going to have 4 neurons in hidden layers. It can be even more. But dropout rate, if it's 0.5, this means 50% of the neurons in that layer. How do we implement that? You can see the dropout. It is as simple as this. Just add for every layer, add dropout point. It's your wish. Again, you want to add it to every layer. You can keep trying it like trial and error. So there is no a perfect way to do it. So usually we add to every layer whenever we apply dropout. It doesn't mean it's been you have to follow that way. So if 0.5 means 50% of 128 is going to drop out 128. That means 64 neurons. It's going to again in the next loop. It's going to be another set of. It can be same or it can be not be same. So if we 64 here, so it means 34, 32. So again 32. Here it means 16. So that is how this dropout works. Early stopping, I spoke about it. So there is a possibility that it may even go beyond a certain limit. That way, the accuracy or may decrease, or the loss may keep on increasing or become constant. That is when this early stopping, you know, are necessary. Even though in this particular script, I given early stopping as separate one. You can see that early stopping, this is how we need to create. And patience, we discussed it, right? So it's going to wait for another 30 epochs. So we have mentioned validation loss. Basically, loss means it should not increase. At least it should be it should become constant, or it should decrease. If it becomes constant or if it keep on increasing, then it's going to wait for 30 epochs. Suppose 1,000 epochs we have. After 200 epoch, it got it became constant or it started increasing. Then in that case, it's going to wait for another 30 epochs and it's going to stop the whole training. So it's not going to go beyond 230 epochs. So even though we have clearly mentioned 1,000 epochs.
Sir, can you explain when early stopping will come in picture? Just like you explained where behind the tree, so like that. Can you give an example for early stopping also?
I already gave an example. Yeah, 85% accuracy. I think you haven't listened. So 85% accuracy, 85% accuracy, and then it can decrease. So I've given the patients true. What's the recording again? So I already explained that idea with an example.
Okay.
So this is accuracy, and if it is loss, obviously it should not increase. If it is accuracy, sorry, if it is loss, it should not increase. If it is accuracy, it has to increase, but if it is constant or decreasing, then it's a bad indicator. And here we have one thing is that every concept I have given the script here, but thing is early stop and checkpoint. The checkpoint is I have mentioned it last. You can see the model checkpoint. I have given model checkpoint here. So how to create model checkpoint? So it's going to keep on saving the model name. It's going to keep on adding some unique value to this and save best only. So it means that it's going to whatever when we stop this when we use with the combination of early stopping, it's going to pick the best model. And even though if we don't use early stopping, and still it's going to pick the best model. But the problem is that just imagine the 1,000 epochs and 200 and 200 after 200 epochs, it started not improving. So then in that case, then another 800 700 epochs been wasted, right? 700 or 800 epochs been wasted. So we are unnecessarily adding a lot of space. So we need to combine with early stopping and model checkpoint. So early stopping, what are the objects that we have created? Just list as a list. That's all. Okay. Even though I have given this as as two separate things. I hope you got the point. All right. The next one. So it's validation loss. If it is accuracy score, if it is classification problem, ACC accuracy. If it is regression, it's going to be auto score. If it is regression and you want to focus on MAE or MSC, you can give that way. Okay. All right. So the next idea is here. Basically, what we did here is in the script. without regulation, with regulation, with L1 regulation, L2 regulation, dropout, early stops, we start comparing one to another. We can see that in this case, MA is very less in this particular L2 regulation. We don't know which will work. So we need to keep here it's more straightforward. So only one method each. But we need to combine, and there is a possibility that we can even try with various permutation combinations, right? You can go for that. And in this particular case, I think this is best. Even though test MA is a bit less in this case, but the train MA is 2 points. So there is a huge fluctuation. Um, all right, the next one is batch normalization. Of course, you can try various optimizers. If it is Adam, you can see that optimizer Adam just in the compile phase. I given code for everything, even for that. I have given code right here itself. SGD, ready, right? That's SGD being used. Add a grad or whatever. So add a grad being used, right? Or I think I have given RMS prop. RMS prop. So you have examples for everything. Just use it as a reference. And the only thing you need to do is when you get the real time, when you get into project, you need to keep trying, the permutation combinations to get the best out of it. So, but get the better accuracy, get a model that has better accuracy and less loss. Compared to which one you need to pick when it comes to accuracy and loss? Loss you need to focus more because the data set that we have taken, we may have better accuracy, but the loss need to be reduced. Suppose if the loss is the loss, what is the loss? The error, right? So if the error is high, even though the accuracy, whatever the data set that we got is better, doesn't mean that it is the best model. So we need to keep on reducing we need to focus on loss also. Loss is a better parameter compared to the accuracy. In interviews, you will get this question. When it comes to the way it fluctuates and the formula for it, you can see that usually what will be the formula for number one this is going to be the formula, the world weight minus learning rate into rho L by rho W. That is for stochastic gradient descent. Of course, the way we take the data set, if we take for the whole data set, it's going to be batch. If we take it in chunks, it's going to be mini batch, the same formula. When it comes to momentum, the additional thing that they have added is this plus V. So initially it's going to start with big step and then it's going to start with a small step. That is how it works. Yesterday I explained that, right? With the parabola, a small. So how that works, the V comes from here. Again, this alpha is one of the parameters that it has to find minus this V is old V. If we start with, in the initial stage, at the first phase, V is going to be 0. And usually it's going to be this one. So in that case, what happens? It's going to be the typical formula, W minus learning into dou L by dou W. And thereafter, the second step onwards, it's going to keep on changing. This is momentum. And this is how it typically going to be. If you look at this one, it's almost same, but it's going to be much faster compared to the stochastic gradient descent. You can see that it's much faster compared to the original one. Add a grad, basically, so it's going to set a very high learning rate at the outset and gradually lower it. So that's the whole idea of the ADA grad. So basically, they take the previous model, previous optimizer, they keep changing these things. Like they initially set a very high learning rate and then gradually lower it. Uh, uh, but in this case, in the case of momentum, it is automatically been calculated. So ADA grad is not widely been used. But one thing that they brought something new is they add this error part wherein it's going to, there is a possibility that it may have this error. And this epsilon is basically error. It's a constant value after being experimented on several data sets. That is what this they came up with. RMS prop, you can see, tends to lower the learning rate too fast, and thus learning rate becomes zero too early. Adagra has this issue. That there's a possibility that it become almost zero at a very fast rate. So what this does is like it's going to sum of square of gradients. So the idea is it is going to consider the previous gradients. If you look at this, is 1 minus beta into the previous weight. This is the current weight. It is going to take some proportion of the previous gradient and is going to add to the existing one. That is the chain that they have brought in RMS prop. And Adam is basically a combination of momentum and this RMS prop, or add even the latest ones. If you look at this, it is very much similar to RMS prop, except that they added this velocity, momentum, which was not there. So Adam is the most popular one for a reason that it performs much better. Another one is normalization. So we have discussed what is normalization, right? So normalization or scaling. Otherwise, we can even call it as scaling. Here, normalization means scaling. See here, the formula clearly tells that it is standard scalar, right? So the problem is that we can even apply batch normalizations. Batch normalizations for every for every layer. Let me, right? So if you look at this, batch normalization is a very rare case that you may not even require. We can apply batch normalization. What happens is, like when the parameter values become too huge, then it has to be scaled down. So let's take the beta B0 equal to some 255 and B1 equal to something like 2.5. Then it has to normalize so that it's going to give an equal importance to all. So we can apply it for all the layers, or it's your wish. But batch normalization is I don't recommend it at all. So I haven't used it in real time. But it is a very rare case. If the accuracy is not at all possible, then better to focus on getting more data rather than applying normalization. That is my advice, because there are enough methods that does almost everything what we do. And moreover, when we apply standard scalar, that itself, give importance to every neuron. So then if there is a case that the weights being disproportionately high and low fluctuation, if you observe fluctuations in it, then we don't really require this. So that by nature, that's how it is going to be. And we have given, and I have given for almost everything. In momentum, we don't have any specific additional methods. The one thing is for the same SGD, you need to add this momentum 0.9. We can be even low, but this is high. This is recommended directly from the one who has brought this concept. So there is no specific method or component for momentum. It is the same SGD. We need to add this one. That's all. In typical SGD, stochastic gradient descent, you are not going to find that. And for where is that? Yeah, RMS prop. Rho is again another parameter that has to we have to add. RMS prop is going to use this rho parameter, and you're not going to find optimizer anywhere here. We can directly mention optimizer equal to this one, copy paste, or else you can leave it because it's going to set automatically. It's going to take in automatically, so you're not to bother about it. It's better to mention inside this optimized equal to this one, just copy and paste. Both will work. And for other optimizers also I have given, but don't choose other optimizers, only use Adam. Just for your information, I have given the other options. You have a complete list here, so I'm difficult to scroll down or scroll up. I've given complete thing. So RMS prop, add a, I already shown you that, right? Add a grad. Yeah, add a grad or Adam, whatever. Automation, batch formations, the way you implement already, we have already saw the script. Save the model. Yeah. Model checkpoint, we already explained you. So it's going to keep on saving wherever you run the script. It's going to keep on saving these files. So there is a possibility that it may take a lot of space. So you need to have enough space for that. Let me execute this once. I don't know where, let's say whether it is the existing one location or somewhere else. Where to cross check that. Uh, okay. So let me go back. I have not the data set. Looks like the data set I have not provided specifically for that. Data set is somewhere else. Right. So, yeah, we can do this, right? Okay. Looking for the data. Yeah, here we have. Um, okay, this is not the one that, okay. Next one is evaluation RFS for um file path must be Keras folder file path. Okay. Want to save right here. So the file path must end in dot keras. Okay. Keras model format is suit file path. So it is not expecting model is not defined. Okay. And I have not imported. All right, I will cross-check the script and re-upload that as well. So it's too long that I need to keep checking it. The model is not defined. So where is this model? Okay, I have it somewhere else. Okay. Yeah, I need to re-execute this and correct the errors, and I'll provide you the script. Basically, should show, I mean, should save right in the file, like wherever we have. It's going to create a folder and it's going to keep on saving this one. So you need to make sure that you delete all the previous ones. Otherwise, it's going to keep on adding space after you executed it. Okay, so that's it on the deep learning part. So tomorrow we will start CNN, convolution neural network. Even though we need to focus on RNN, but CNN is mostly for images or videos for computer vision problems. But yet we will discuss it because generative AI is going to have even images and all. Um, but right now we don't have any open source models that are good enough. So we need to predominantly focus on RNN. So I request you to go through PDFs once before you attend the session. Even if you don't understand, that's fine, but at least you will get a map in your mind, right? So tomorrow, okay, that's it for today. I'll correct this, I'll correct the errors, whatever. I think it's not really the error. We need to execute all. That's the only thing. It's not really an error. So I need to execute the previous stuff. So I want to demonstrate this and show, like, and want to find out whether, where this will get saved. But I need to keep looking for the other one, where we have this model. All right, That's
So
it for today.
what's the main difference between this ANN, artificial neural network, and CNN?
CNN is for images or videos. So when we directly apply deep neural network on images or videos, then it's going to explode when it will have billions of inputs. We need to compress it. We need to extract only the important features and compress it. That is why we need a
For
CNN.
images and videos, CNN. RNN is for?
Text or time series. So for generative AI, LLM models are based on RNN architecture. Of course, there are more advancements. RNN is the base.
Okay.
All right.
Yeah,
Thanks for joining.
sir.
Yeah, go ahead.
Yeah, sir. Tomorrow and day after tomorrow, I will not able to join because I'm going to my hometown. So,
You're not going to
uh,
join. All right.
yeah.
Watch the recording.
Yes, sir. Sure.
Okay, thank you.
Thank you.